Hello and welcome to Lecture 16. Here we're going to cover section 23.5 of Survey 11th edition. This will be part 1 of a lecture on the topic of thin lenses. So to get started, let's take a look at our objective. Here we have one topic that we're covering, so we have one short objective, and that's simply to learn what aspects of thin lenses determine the type and location of the image created by that lens. And the idea here, or the ideas, should be very similar to those found in the previous lecture on spherical mirrors. So many of the conventions about focal length, image type, even the idea of what types of mirrors tend to make what types of images, all those sort of trends should carry over to this discussion. And so you should start recognizing how to make comparisons between mirrors and lenses. So first, though, let's get one of the key ideas of the thin lens out of the way, and that's why we call it thin. So a thin lens is a simplified lens where the thickness is assumed to be negligible. And why we make that simplification is because that way we do not have to worry about multiple refractions, that it would be at the first interface and second interface of the air to lens, or whatever surrounding fluid to lens, and then back to that surrounding fluid. Instead, we only have to make a single refraction, or you can think of it as taking both refractions and condensing them down to one. So, to illustrate that idea, let me show here what real refraction would look like, and then what the thin lens approximation looks like. Okay, so here we'll do it in blue. So for refraction, like we were seeing in the previous chapter, for prisms, we would have an incoming ray like so at the first surface, because here we're going from N1 to N2, and N2 is going to be a higher index of refraction. Really, most of the time it's going to be air to glass. So we'd have a bending towards the normal, so it'd bend like so, and then go down into the glass. And the normal direction would be something like this. Okay, so let's try to get the normal like so. I'll zoom a bit more on this. So there's our normal direction. And here let's have our normal direction as well. All right, so both of those would represent the normal. So we have a bending towards the normal, which we can see clearly, right? This between these two angles. All right, theta 2 being smaller than theta 1. And on the way back out, we would bend away from the normal, so it would further bend like so. Okay, with this being our last two angles. Okay, so that would be true refraction. Okay, so we can label that as such. So true refraction. But that would be a very complicated situation, because we obviously have a curve here, assumed to be a spherical curve, so a slice of the circumference of a circle. And so we would have normal vectors, which would be a function of that location on the curve, right? Because they change. Of course, here the normal vector is at a completely different angle than the normal vectors that we drew. And so it becomes incredibly complicated. It often doesn't make sense as long as the lens is thin enough. So instead, we take a simplified version. So we'll have a ray coming in again. I'll draw it right to the center of the lens, and then just have a single refraction. So instead of the refractions being represented where they're actually happening at the two interfaces, air to glass interfaces, we just draw a refraction right in the middle, and that encompasses the entire point. Okay, and that would work if the lens itself was, actually just a single sheet. Now, of course, the issue there is that if it was just a single sheet, if it was just of negligible thickness, then it wouldn't have curvature, and we need the curvature. So it is a simplification. In its very nature, it is introducing some deviation from reality. But it ends up being a very accurate simplification in many cases. So this is the simplified refraction. Let me spell that correctly. Okay. So what we want then to point out in that definition that the simplified where the lens thickness is assumed negligible, and then to say that this allows for consideration of just 1 point of refraction. And I'm sure that makes sense. I've explained it thoroughly. Okay, so our other key terms are the 2 types of lenses. Those are converging lenses and diverging lenses. Okay, so first, just kind of a general statement about them. So a converging lens is any lens that is thicker in the middle. So it turns out that if that is the case, then the rays converge. All right, and the name is simply that. The name should invoke the idea of rays coming together and converging on a single point, because that's exactly what the converging lens does. It can focus rays. So you think of starting a fire with a magnifying glass, then that tells you that the magnifying glass is clearly a converging lens because it's able to focus all of the rays of sunlight on a single point. Okay, so that is thicker in the middle, good. So we can actually say focuses the rays to a single point. Okay, and to be some more specific there, I'll say focuses parallel rays, because in the case of the sun, and this is an idea we'll kind of come back to in more detail when we talk about telescopes in a later chapter, but in the case of objects that are very far away, those faraway objects are absolutely represented as parallel, and so, you know, as such, then we can they would always focus on a single point. However, if objects are closer than the sun, so you know, not effectively infinitely far away, but instead if you have an object that's very close to the lens, then you can actually create a virtual image with that converging lens. So just like you have concave mirrors can create both virtual and real images, likewise, converging lenses can create both virtual and real images. So they can create, and primarily going to create real images. Well, maybe not primarily, but a lot of the time. So it can create real or virtual images. All right, so in the case of using a converging lens for magnification, that must be a virtual image, because remember the human eye can't see real images. And so that virtual image is what we would actually be visually able to discern. Okay, and then the other key idea here is that the focal point is positive. So the focal, I'll say focal length, is defined as positive. Okay, and here's an important thing. That would be, as defining a positive, that means it's on the opposite side of the lens from the object. Okay, or from the, we'll say from the incoming light. So opposite, no, I'll say object, opposite side of the lens from object. Okay, now here's the thing, right? I'm saying that that's defined as positive. Notice that that is in stark contrast to how we defined positive for the for mirrors, because something was positive if it was on the same side as the object. So we still have sign conventions here, but the sign conventions are swapped compared to mirrors, because for the convex lens or convex mirror, the focal point was actually behind the mirror. It was within the wall, which is the same as, say, a planar mirror. In both those cases of mirrors, the focal length is defined as negative because it's behind the mirror. Okay? So what that gives us then is we have the idea that anything that is on this side is negative, okay? And then anything that is on the opposite side is positive, okay? And in both cases, let me draw an object. So I'm going to draw an object for both lenses to help illustrate. I'll draw one. Okay, so for the converging lens, we'll put an object over here. All right. Let's make that a little better. Okay. And then for the diverging lens, I'll put an object in here. Okay. So those are two cases of having the object. The object really sets the sign. I think that's the best way to think about it. And so having the object on this side means that anything that is on the same side as the object is negative. Anything that is on the opposite side of the lens relative to the object is defined as positive. And so that means that the focal length for the converging lens is this length here. So this absolutely would be defined as f. And you do really have to pay attention. I highly recommend at least paying attention to all these signs. Make your life a lot easier. All right? Okay, so that's it for the converging lens. We're going to then kind of show the counterpoint with the diverging lens. So this is any lens that is thinner in the middle. Okay, and this type of lens, it causes the rays to diverge. All right, so parallel rays are caused to diverge. So I'll say really any incoming rays are going to be diverged. So any incoming rays are diverged. And by diverged, I mean they're just sent off in directions where they will never cross. Okay? And the focal point is defined to be negative. So the focal length is defined as negative. Okay? And that would be on the same side as the object. Okay. All right. And let me just highlight that negative, positive. So negative, positive. So then you can see then really the mirror that was like the converging lens was the concave mirror because it had the positive focal length and it created both real and virtual images. And then the mirror that was like the diverging lens was the convex mirror that only created virtual images and had that negative focal length, right? So and because they really kind of did similar things. The convex mirror causes rays to diverge, whereas the concave mirror can do both. Likewise, that converging lens can do both. It can both cause rays to diverge or converge. Okay. So then going back to just draw some principal rays and illustrate this idea. Let me just draw a few principal rays for our two lenses. All right. There we are. All right, so for this lens, remember there's the three principal rays. There's going to be one that goes, that comes in parallel and then goes through the focal point. And so what that would look like, and I'll have all the rays be from the top of our object. So we'll have a ray come in, and then it would have pass through the focal point like that. All right, so that would be ray number 1. The other type of converging ray was one that passes through the opposite focal point and then comes out parallel. And so that one would look something like this. Okay, C. Okay, and let me extend the ray number 1 a little bit. So this one go down a bit further. All right, close enough. Nearly close enough. There we go. Okay, and then the last of the principal rays would be one that just passes through the center or the intersection of the optical axis and the middle of our thin lens, which would be this point right there. So we'll have a ray that comes down. Oh, I should label this as the second of the principal rays. All right. And then the last one will be this one that comes down like so, right through that point. So something like this. Yeah, looks pretty good. Okay. And obviously all three of those rays should converge at the same point, and that's, you know, so they do approximately. And that means that we would have an image. So let's label this one 1, so they're all kind of out of the way. That means we would have a inverted image, like so. Okay, there would be our image. And our image is inverted, which means it's real, because remember, only upright images are virtual, or all virtual images are upright, at least primary images. When you make an image from an image, then those rules can change. But when you make a single image from an object, then your real image, the one that the human eye cannot see, but that would activate photoactive paper or show up on a screen, that image must be inverted. Okay? So this is a real image. And notice here, when I drew it, I got a real image using simply my ray diagram and following the rules of the three principal rays. Had my object been located inside the focal point, I would probably get a different result. And you have a question I'm going to leave for you that you can solve on your own, where you can find out that indeed is the case, which is good practice with ray drawing. Okay, so the last two things I'll label in this picture are just S and S prime, right? Because I just want to call attention to those. All right, so we got that. Okay, so remember, S is the length or the distance to the object. In this case, it would be the distance from the middle of the lens to the object, whereas before it was the distance along the optical axis. For mirrors, it was the distance along the optical axis from the object to the surface of the mirror. Here it's to the middle of the lens. And so this would be our S value right here. Right, so S for the object. And then S prime for the image is going to be the distance from the center of the lens again to where the image is found. Okay, so then we can see that in this case, creating a real inverted image using a converging lens, I got a S prime that has a sign that is positive. So getting a S prime that is positive tells me it must be a real image. And again, that's going to show up in the magnification formula, which I'll call attention to in just a minute. But before we quickly go over the formulas, let's just do our case here for an example of a diverging lens. Okay, so I should expect this one to create a virtual image. Let's see how that happens. Okay, so in this case, our focal point is going to be here on the same side as S. And I'm going to show you all that. So right here. Okay, so there's F. F is defined as negative, and it is on the negative side, so the rules are consistent for lenses. Anything on, basically, because we're always really going to put the object on the left, and so you can think of anything on the left as being negative and anything on the right being positive, which is nice because it's consistent with a coordinate axis. Okay, and so there's our negative F, and so then we have to think about how, what our rays would look like. So if we draw our three principal rays, we're going to have one that is going to come in parallel, and then it's going to then pass through the focal point. Well, what does that look like? Well, right, this, you kind of have to think about this a bit more carefully with these diverging ones. So it would come in parallel, and then it would have to be as if the ray passed through the focal point. Okay, and so what that means is that we'd have the ray diverge, but we'd have a continuation of the ray that effectively passed through the focal point. So there would be something like this. That'd be the diverging part, and then continuing down, right? That's how I know how to make what angle to draw that diagonal line at, is I basically draw that line straight from the focal point up through the point where it touches the parallel ray, and then I just want to make this section dotted to make it obvious that that's a continuation of the ray and not an actual ray of light. Okay, so that is the first principal ray, the one that comes in parallel. The second one was the one that passes through the focal point and then goes parallel. Okay, so that one would be like so. All right, so that one's going to want to come out parallel. So, okay, yeah, so it'd be like this. Okay, and no, that's not quite right. So what am I doing? Let's see, so this one, this is one that would be passing through and then come out parallel. So it should be like this. And then come out parallel like that. Okay, let me just think about this. So we have the one that would come in parallel. The last one will be easy. That one just goes right through the center. Just want to make sure I'm doing this one right. So this one is the. So I did the one that came in parallel and then got sent off. So that's fine. Okay. And okay. And so if we think then instead we'd have one that would be passing through the focal point. Yeah, so this is the one that it would be as if it was going through the other focal point. Okay, so that is the correct idea, and that's kind of tricky to think about why that is. So let's draw it out, and I'll elaborate on it briefly. Okay, so then this is not the actual ray. This is just a continuation. Okay, and then this would be, so then let's draw the actual ray. Okay, oh, I need to make it dotted in one more section. So something like that, okay. And then we'll have it come out this way. Okay, so that would be ray number 2. Okay, so the idea is it's the ray, and I think that's what I was stumbling over just now. It's always the ray that passes through the opposite focal point. Because there's always 2 focal points. Notice in all the images I made sure to draw 2 focal points. There's one, and it's because it's a symmetric lens, right? But there's one that is at least these types of lenses are symmetric. There's one focal point which is the defined focal point for that type of lens. So in this case, that is positive f. Now there's also a negative f, right? I could call this the negative f of the converging lens. Okay, I'm not going to. That's not the one that I would use in the lens formula. But it is numerically, it is negative f. Likewise here, negative f is the one that I use in the lens formula, more than just a minute. And this, however, is still f. It's just not the one that shows up in the lens formula. And so when we're drawing our 3 principal rays, we always draw one ray, like we did for up here. We draw one ray that's parallel and then passes through the actual focal point of that lens. And then we draw another ray that passes through the opposite focal point of the lens and then comes out parallel. So for the diverging case, the one that came in parallel has to have a continuation that passes through the actual focal point. The lens that passes through the opposite focal point, that's this one right here. So you can see then that we're actually following the same rules, even though the effect ends up being different because, of course, the sides of the lens that are defined as the actual focal point and the secondary focal point are opposite for the 2 types of lenses. So let's do our 3rd and final ray. This is the one that's going to come through the middle. Okay, that looks pretty believable. And that would be ray 3. So first of all, when we look at this, we can see right away that there's totally divergence here, right? The rays are not coming in and overlapping. Right? They're not going through the lens and overlapping. After they head through the lens, they go off and they're never going to cross again. They're just spreading out into space. Right? They'll never cross as they continue on. But there is still an image formed. In fact, there's a virtual image that the human eye could see. Well, how do we find that? Well, we have to do a continuation of this ray that we haven't, and that would be a back continuation. So I'll do that as a dotted line rather than a dashed line. And so that one would go back this way, like so. And so where the three rays cross, which is approximately right at that point, that's where our image would show up. So this would be our virtual image, okay? And so that would be our S prime distance from the center of the lens. So if I then was to label the S, S prime, and so on, this right here would be S, always positive, okay? And then we have S prime right here. And in that case, S prime is defined as negative because unlike the object distance S, it doesn't set the coordinate system, and it's instead, it's subservient to the coordinate system, and it's on the negative side because it's on the same side as S. And so that tells us that it must be a virtual image. It has a negative S prime, and which means it must be upright, and indeed it is. Okay? So take a look at the formula then. So this would be the thin lens formula, which you notice is the same as the spherical mirror formula. So we can use this formula for both types of optical devices, spherical mirrors and spherical lenses, because here we are dealing with slices of a sphere, in both cases of the diverging and converging lens. So we can use that same formula as long as we're careful, as I've mentioned a couple times, as long as we're careful about following the sign conventions, respectively, for mirrors and lenses. Okay? So in this case, it's just a matter of thinking about when S prime is negative, when S prime is positive, and so on. Okay? And we can see then that as far as magnification, it's also the same rules. So this is the magnification factor. And by saying it's the same rules, I mean that if we have a positive magnification, then it's upright and it's going to be virtual. Okay? So if we go here, positive means upright and virtual. And then negative here means inverted and real. Okay? And that was absolutely the same. There's no change in the rules at all for mirrors versus lenses for using that formula. Okay? All right. And so you can see that in the two cases, we would have a negative and positive magnification respectively. Now again, that doesn't tell us anything about the numerical value of the magnification. In fact, for the converging lens that I drew, the real image would have an M that's greater than 1 because it's larger than the original image. It's taller, but it'd be a negative value, but its magnitude would be greater than 1. And then for the magnification for the diverging lens, in that case it's a positive magnification, but the value would be less than 1 because our upright virtual image is smaller, as the ray diagram shows. And again, the ray diagram isn't good for finding the value. The ray diagram is good for kind of checking your work and just making sure you understand the subject. So, it's a question I like to ask. The formula, the thin lens formula and magnification formula, that's how we actually find the numeric values. Okay, that's our sure proof way of doing it. So we have one of the formula to present here, in two forms. And so what this is right here, this is a new formula. This is not something we saw with mirrors. This is called the lens maker formula. And what it tells us is if we know the curvature of the lens slices that we're using to make a convergent diverging lens, then we can find the focal length of that, made, hence the maker part of the name, of that made lens. Okay? So the idea is that if I want a lens that is a diverging lens that has a particular focal length of 10 centimeters or something, then that means I want my f to be negative 10, because that's the only way it's going to be a diverging lens is if f is negative, by definition, remember. And so that means I'd have to choose values of R1 and R2 to represent that negative, to get that negative. But how does that work? What is R1 and R2? Well, that's the radius of each half of the lens, okay? So this is the radius of left half of lens. That's always R2. And then R1 is the radius of the right half. Excuse me. I meant to say this is the right, because you read from right to left. Okay? And this is the radius of left half of the lens. Okay? So to show that in the picture above for the diverging lens, R1 and R2 would look something like this. Okay, so then R1 would be somewhere over here. This could be R1, right? Probably not exactly drawn to scale, but you get the idea. And then R2 would be over here. Okay, because again, they're slices of a circle. The idea is simply that we would continue, this circle like this, and its radius would have some center, right? Likewise, if we continued the circle that represents the left half of the lens, then there'd be some big circle, and then R1 would be the radius of that circle. And then, of course, this is being, a small slice of the circumference, as I said before. So, okay, now back to the sign convention, because the sign convention holds here. So you don't have to, that whole idea that this is the negative side and this is the positive side holds for everything about lenses. So what does that mean? Well, that means that R1 is negative and R2 is positive for this diverging lens. Okay, well, if we look at that, then we'd have 1 over a negative value minus 1 over a positive value, which means this whole bit inside the parentheses would have to have a negative sign, which is great because that means that when we actually solve for it, we're then going to get a value of f that is negative, okay? Which we better because we have a lens that is thinner in the middle. And that's a diverging lens. And I told you that the sign convention for a diverging lens is that the focal length is defined as negative. Well, now you really see that this lens maker formula shows why we define a focal length as negative for a diverging lens. Because really it comes from the idea that a radius that points to the left is defined as a negative radius, and a radius that points to the right is defined as a positive radius. Now R2 isn't always positive, neither is R1 always negative, okay? You just have to make sure that when you sum their reciprocals, or rather have the difference of the reciprocals like this, that the sign then gives you the right type of lens with the right sign of focal length. Now, there's one thing I haven't labeled yet in this formula, and that's simply the n, and the n is the index of refraction. So the idea here is that if you were making a lens out of glass that had an index of refraction of 1.5, then you would have to put in your 1.5 minus 1 in order to get the correct focal length measured in meters, okay? Because you'd want to plug in your radius in meters and your focal length in meters as well, okay? Now, alternatively, since there's no other units here other than the lengths, because the index of refraction is unitless, you could put everything in centimeters and then get a focal length that, or put both your radii in centimeters and get a focal length that also comes out as centimeters. Just be aware of that, okay? So, that's the lens maker formula. Why do I have another version below? Well, because the second one is the lens maker formula for a substance that is surrounded by a fluid that has an index of refraction other than 1. So lens maker formula for lens surrounded by substance with n not equal to 1. Okay? Whereas here, the idea, and that would be n2, by the way, that'd be n2. The idea is that for the first one, for the basic lens maker formula, it is assumed that that lens is in air. And so then, in that case, the surrounding index of refraction is effectively 1, and so therefore, we don't have to consider it. But if we have a lens in water, that's the biggest, most common example, where the index of refraction is 1.33, well, that's definitely not 1, it's significantly different, and so we have to take that index of refraction into account for making our lens. And so that's why N2 shows up in that formula and then N2 is index of refraction of surrounding substance. So you can see it's just a slight variation on the lens maker formula for those wet lenses. All right. Okay, so that concludes part 1 of this lecture. In part 2, I will go over